All right. So what we saw on Tuesday, if you were here then, is that a derivative, and we didn't even really focus on it and calling it a derivative, we called it the slope of the tangent line, but it turns out they are the same things. So just as a little reminder of our definition here, we're going to say that f prime of x, this is called the derivative of f at x. So this f prime means derivative. That this is equal to the limit as h goes to 0, f of x plus h minus f of x divided by h. And remember that what that is doing is it is calculating the slopes of these lines as the sort of distance between the 2 points gets smaller and smaller. Right? So like this mechanism, this graphical tool for finding the derivative is what's represented with this definition. We ended by kind of referring to that f prime of x as the derivative, but we didn't really use it very much. So here today we're going to kind of use that more, and moving forward we're going to use f prime of x. It also is sometimes represented as just the slope of the tangent line. So keep that in mind, that this f prime of x really means both of these things. It is the slope of the tangent line at x, which is also defined as this limit. So, well, let's see if we can find, we did one example, but let's try a different example. Let's try, let's let f of x equal 1 over x. And let's find f prime of three. So there's the geometric side of this, like the tangent line and the curve and how they all fit together. But then there's also just like the algebraic side, like, okay, I have a formula for this derivative and I'm going to plug it in and calculate that formula. We want to be conscious of both of those. We want to really be finding or calculating the value from the algebra and the definition. But at the same time, we want to keep in mind what we're really calculating is actually the slope of this line that sort of mirrors or skims the function at this particular point 3. Right? Both of those interpretations are important for us. So to calculate this, we're going to use our definition here. F is 1 over x, so f of x plus h is going to be 1 over 3 plus h. So right, this part here is f of 3 plus h, because this is my function f. And then that's divided by h. So that's that definition. We know that every time, this is going to give me, oh, did I write infinity there? That's not good. 0. 0. Always h goes to 0. We know from our definition that every time if I try direct substitution, I'm going to get an indeterminate form, right, where both the top and the bottom are going to 0, and we can see that very quickly with this one as well. So every time I'm using this definition, my immediate step is to try and change it algebraically. I need to use some kind of tool to rewrite this so it takes away the indeterminate form. There's no square roots here, so I wouldn't use conjugates. There's no polynomials, so I wouldn't use factoring. There are 2 fractions, so that's really the approach. That's the clue here for this one. I'm going to get these to be common denominators, so I can add those fractions together and multiply that side by 3, this side by 3 plus h. That's going to be 3 minus 3 plus h all over 3 plus h all over h. Okay. And of course, still the limit as h goes to 0. But I'm just focused on the algebra part here, not the limit yet. So these 3's are going to cancel. When I'm dividing by h, that's the same as multiplying by 1 over h. So I have negative h over 3 times 3 plus h times 1 over h. Those cancel. And that's good. That's our key, right? When we cancel that thing that's making both the top and the bottom 0, that's my clue to now try direct substitution again and see if I can calculate this limit directly. And in this case, I can, right? When I put in now h equals 0, I get minus 1 over 3 times 3, or minus 1/9. Graphically, we have the function 1 over x, which looks like this. And we're looking out at 3. It's hard to tell exactly what that would be, but negative 1/9 is a pretty reasonable number, right? Notice that this tangent line would definitely be negative, right? It's going down from left to right, and it's a pretty low slope, so it's pretty close to 0. So minus 1/9 makes sense, and that always should be the case, right? If I got an answer like 3, that doesn't make any sense, right? That answer can't fit with the situation. So there is a little bit of a check, right, on these in some cases. Any questions about that example? Okay. Now, what if I took the same function and asked you to find about f prime of 2? And then after that, what if I said f prime of 1? And you could just start over and play the same game again and again and again and work your way through each of these limits. Each time you'd get a slope and you'd answer the question, but you can, I think, imagine that it's kind of a pain to have to keep doing this over and over for different values of x. So what might be nice is to say, what is f prime of x? Can I come up with some function where if I give it the input x, that there's a formula that'll tell me what the output is, right? And the output in this case, of course, is the slope of the tangent line. But then I don't have to go through the whole process over and over again. And I certainly can try and do this. Take the limit as h goes to 0 of 1 over x plus h minus 1 over x over h. So I'm basically doing exactly the same work. I just have a dummy variable here, right? This x, rather than having a specific value like 3 or 2 or 1 or negative 1/3 or whatever other value I might have. So just like before, I'm going to use common denominators. It's going to really reduce the same way. X minus x plus h, x times x plus h over h. The x's cancel, the h's cancel. and I get -1. The h goes to 0. I get -1 over x squared. So notice, if I knew that formula, I could tell you what f prime of 3 is, right? It's going to be -1/9. And now with this formula, these other questions are trivial, right? What's f prime of 2? Well, the formula says if I go through this whole limit process, I'm going to get -1 over 2 squared, right? Or -1/4. F prime of 1, same game, -1 over 1 squared, or -1. Give me any number you want. This formula, it turns out, is going to return me the value of the derivative. And what's kind of amazing here is that this formula is telling me the slope of the tangent line at every point x, which I think, you know, when you're starting out, it feels like, how is that possible? Like, if I look at this curve 1 over x, I mean, it's like, it feels sort of like each of these values is really different. Like, I'd have to, it's a different point, like there's a different process there. How can I have one formula that tells me that at all those points? But we've got it. It's right here. And this is called the derivative. So f prime of x for our given function f of x is -1 over x squared. And this will turn out to be very useful for us. It's called the derivative because it's derived from, or it comes from, some other function, right? So that's maybe a change for some of you, is that you've worked with functions before, but typically it's just f of x equals y. So you have an input and you have an output, and you know, that's it. They don't really mean anything other than this x connects to this y. But here, all of a sudden, our outputs have a meaning. Our output means the slope of the tangent line to this original function. So the outputs have a value to them that they, it can take a little bit of work to think about. You're used to that output just being an arbitrary number, but now that number has a physical meaning. It means about the slope of our original curve. Questions about this or this example? As always, the chat is fine, or you can do private chat if you'd like, or chat with everybody if something comes up. Okay.
I have a quick question.
Yeah, great.
If you're given an equation for f of x, like I don't know, x squared plus 2, and you're not given an x value, how would you find the derivative of that?
Yeah, good question. So the derivative, and this is, maybe I didn't define this so carefully, but the derivative is, we're going to call the derivative the actual function that gives me the slope of the tangent line. So the value of the derivative changes at different, well, the output of the derivative changes for different x values, right? The slope of the curve is not the same, right? Over here, I can see the slope is positive, and over here, I can see the slope is negative. So the derivative of this, which is the slope of the tangent line, is going to depend on where we are. It depends on x. Notice that's true here too, right? The value of this derivative depends on x. Different locations are going to give me different slopes to the original curve. So if, and I think your question sort of had two good parts there. If I ask you for what is f prime of x, like what is the derivative, what I'm actually looking for there is the function, right? So what is the function that gives me that that derivative, right? Or the slope of the tangent line. You could also be asked, what is f prime of 2? And that is both the value of the derivative at 2, and also it's the slope of the tangent line at 2. So they're all interrelated very tightly. They're the same things. But this is, the interpretation of this is a little trickier because it's something that changes, right? It's a function. Its outputs are always the slope of the tangent line. Let me give you an example here, maybe. What if I tell you, let's just call it g just for variety. What if I tell you g is 5x plus 2? What is g prime of x? Anybody have a guess what g prime of x is? You could go through the definition and figure it out, but you could also figure it out, and you may not be totally sure what the tangent line is, right? 5x plus 2 is this line. Turns out the tangent line at any point is going to fall on that same line. The goal of the tangent line is that it sort of matches the existing function at that point. So for this function, no matter where I am, the tangent line is going to fall right on that line. So the derivative at this point, at any point, is going to be 5. Whether x equal 2 or x equal 10, the slope there is always 5. I'm not positive if that answered your question or not.
It kind of did. I think that if I go through the equation or the definition, I could figure it out too.
Okay. I mean, I think some of it's the terminology, like how do we refer to it, and then some of it is yeah, running through some examples will help you see it. But what you're shooting for here is, again, some formula that gives us the slope of the tangent line at any point. Let me give you a different example. Let's try this one. Let me not call it F, let's call it G and H. So here are two functions, G and H. One of them is a graph of the derivative of the other. So one of them, either H prime of X is equal to, sorry, let me write that differently. H of X is equal to G prime of X, or G prime of X is equal to H of X. That's the same thing. Or G is equal to H prime of X. So one of them is the derivative of the other function. Remember, the derivative is always outputting the slope of the tangent line to the original function. The outputs, right, are the y values. So when I look at this graph, or these graphs, what I'm looking for is some sort of easy points to try and figure out how things are matching up. And the easiest slopes to find are the slopes where it is horizontal. So when I look right here on this function g, I see that its slope is horizontal. And the slope of a horizontal line is 0. So its derivative should have what y value? 0, right? Because that's what the derivative is. The derivative should be outputting the slope of my original function. So right now, just from that one point, it looks like h is the derivative of g. Now, I don't know for sure. I've got to figure out some more information. But notice here's another point. Notice right there, g is also has a horizontal tangent line, which slope is 0, and the value of h right there is also 0. So there's another point. So this is looking pretty good right now. What is the slope of g right here? What is the slope of the tangent line to g right at that point? Think about that for a second. See if you can estimate that. Can't calculate it. There's no scale even on this graph, but can you estimate what the slope of that line is? You should have estimated something about 1, right? It looks sort of like a 45 degree, which has a slope of 1. And what is the value of h? I mean, again, there's no scale there, but it certainly is positive, and it could be positive 1. So it's looking quite good that h is actually the derivative of g. What are the slopes here of g? Every point along here has a tangent line whose slope is going down, right? Those are negative slopes. Notice the corresponding y values of h are all negative values. So this function h is matching up with the derivative of g. Let's see another one of those. Let's call this one f. And let's see if we can sketch f prime of x. So just like before, it's a very useful strategy. Start by finding where your function has horizontal tangent lines. And you can see there are 3 spots here, right, where there are horizontal tangent lines. At each of those spots, the derivative must equal 0. That's the whole point of the derivative. It gives me the slope of those lines. Since those lines are horizontal, their slopes are 0. So at each of these x values, my derivative is equal to 0. The next major question is this derivative then positive or negative over each of these little intervals? This kind of breaks it up into sections. So over this first part, the slopes of all the tangent lines here are positive, right? This function's going up. So the slopes must be positive, which must mean they must be up here, right? These are positive values. So without getting too detailed about exactly where they are, it should look something like that. Notice here, the slopes are all negatives. The function's going down, so the slopes are negative, so they're going to be below the x-axis. Here, the slopes are positive again. And here, again, these are going down, so the slopes must be negative. Now, you could have drawn something, more like that, or there's lots of different versions in terms of the magnitude. but the positives and negatives are not negotiable, right? Those have to match with the function. It's not somehow like the derivative is like a version of the original graph. It doesn't work that way. I mean, sometimes it might look kind of like the original graph, and sometimes it might look totally different than the original graph. It's just, you don't know until you start to try and do it. And the way we figured out is really, like I said, it's a point-by-point sort of check. Sorry. It's looking at each point and trying to figure out what's the slope of the tangent line at each of those points, and then trying to match that up with the original graph. Questions about those? 5, I don't know. Did I say 5 or could have been from a while ago. Questions about either of these examples? Okay, let me look here for a second. I'm gonna just take a look at the homework and see if I've covered what I had to. Yeah, I gotta talk a little bit about one more topic here. Okay. So the other kind of question is, when is a function differentiable? So when can you find its derivative? Can you find the derivative all the time? Or are there some functions or spots where it's not differentiable, right? And remember, the derivative, we'll write it again because you guys should know this. The derivative is a limit. And we know that limits don't always exist. So it certainly seems likely that there are some places or situations where the limit may not exist. Right? And if the limit doesn't exist, then we say it's not differentiable. So if the limit as h goes to 0 does not exist, then f of x is not differentiable at that point. Just like continuity, it's a piecewise property or a pointwise property, meaning that a function can be differentiable lots of spots, but then fail to be differentiable at some other spots, right? And those spots are each point. And so the question is, okay, well, when does it fail to be differentiable? And it turns out there's a couple of situations. If f of x does not exist, then f, and let me make that, let's call that a, f prime of a does not exist, then f of a, even read my writing here, right? So if f of a does not exist, then f prime of a does not exist. So in other words, if the function fails to exist, then it's not going to be differentiable there. You can't have the derivative or the slope of the tangent line if there's a hole in the graph. If the graph doesn't even exist, then there's no way to figure out like what the slope of the tangent line would be. It also turns out that if the limit as x goes to a of f of a does not exist, then f prime of a does not exist. And that's where you might have a situation like this. So there's a spot where the limit doesn't exist. If the limit doesn't exist, then it turns out you can't do this derivative limit. It won't work out. And it's because, like, what's the tangent line at this point? Well, it's very unclear because the graph doesn't look like a line at that point. It's just like the end. It's stopping. So there's no conception of what a tangent line might be at just a point like that. And so it turns out that if f of x is not continuous, that implies f of x is not differentiable. So if it's not continuous, it's not going to be differentiable. However, there are some other situations where it will fail to be differentiable even if it is continuous. So it's not enough to be continuous. Other places it will fail to be differentiable are if there is a sharp point like this. That function exists there, the limit of the function exists there, that's all fine, but the derivative does not exist because the derivative is the slopes, and the slopes make a really rapid change, like an instantaneous change from going one way to going the other way. And so when you try and find the limit there, it turns out you're going to get totally different values when you come from the left and when you come from the right. So that the one-sided limits won't exist and the limit won't exist. So this is not differentiable at that point. And also the other situation that we can run into is we can't have a vertical tangent line. There are functions like that. This is the cube root function, or a version of my interpretation of the cube root function. Turns out right there, right at 0, there is a vertical tangent line. So that also is going to be not differentiable there. Because what's the slope of a vertical line? It's not defined. So the derivative is not going to be defined if the function has a vertical tangent line. This still is a function, but just right at that point, it has a vertical tangent line, so it's not differentiable. So you want to watch out. Those are really the two main other situations. Any discontinuity, it's not going to be differentiable. But even if it's continuous, there are a couple spots where it can fail to be differentiable as well. Sharp points are probably the most common failures, but you'll also see that occasionally with some vertical tangent lines. Okay. Any questions about differentiability? I go through the proof of this, why that limit doesn't work in the lecture. So that I think that's maybe worth looking at, but the takeaway is that it doesn't work for a sharp point. You can't calculate the limit, or the limit doesn't exist. And be careful here. So this is getting back to the same thing we talked about on Tuesday, is that the limit of the function exists, right? There's no doubt what this limit is. It's this y value, right? The function is going towards that y value from the left to the right. That's fine. It's the derivative that doesn't exist there because of the sharp point, right? And the derivative is also a limit, but it's a limit of what's called this difference quotient. So it's not just looking at what the function's doing, it's looking at what these slopes are doing. And that's not quite the same as what the function's doing.